call it, from Zoom. So as mentioned by Vita, that this morning we start again Friday seminar organized by our department and supported by Indonesian Geological Association, BRIN, Dongeng Geologi, and also supported by Asproditegi. This morning we learned something different from Sam. He is a PhD student from Royal Holloway University and soon will move to what university. One of the supervisors is also here, Dr. Alvin. Thank you for your coming. Sam will talk about something different or different perspective about Citarum River. This morning we are not talking about contamination, we are not talking about the pollution of the Citarum River, but we will learn something about mineral, chemical stratigraphy from the sediment coming from Citarum River. I think this is something new and something different what usually we do in Indonesia. So, okay, without further ado, I would like to invite Sam to deliver the speech. I think that's all from me. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Mr. Mirzam. Honorable guests, ladies and gentlemen, our speaker for today is Mr. Samuel John Holmes from Royal Holloway University of London. Good morning, Mr. Samuel. It is certainly an honor to hear about your research, and discuss it more with us. And without further ado, please welcome Mr. Samuel John Holmes to deliver your presentation.
Hello, Kathy. Selamat pagi. Good morning, everybody. I'd like to thank everybody for coming in and joining us on Zoom for a start. And I'll try to dive in fairly quickly. My project's title is Assessing the Impact of Sediment Capture Behind Hydroelectric Dams Using Mineral Chemical Stratigraphy. This is part of a broader set of projects in the UK under the GeoNet Zero CGT, my Centre for Doctoral Training. All of the projects within that are based on the idea of moving towards green energy and transitioning towards a net zero economy in the UK. And where possible, we are trying to look for applications that work worldwide. In my case, I'm looking at hydroelectric power, which is what's brought me to Indonesia. You have some very good quality hydroelectric dams running up the Citarum River and obviously several more coming in elsewhere, which makes it an ideal opportunity for me to study hydroelectric that already exists and potentially have a look at some upcoming hydroelectric systems. So in the United Kingdom, we have about 4.8 gigawatts of power annually generated by hydroelectric power. Compared to Indonesia, you're already doing around 6.8 gigawatts, which blows us out of the water by a good third. On top of that, our hydroelectric power is very steady. We're not really building any new run-of-river hydro, whereas you have several new schemes coming together, particularly in Kalimantan around the new capital. On top of that, many of our new projects that we are building are pumped hydro. So rather than looking at primary power generation, we're looking into essentially using reservoirs as batteries in combination with our existing renewables. So in the UK, we have a little bit of solar power, but we're a lot rainier than you are in Indonesia. So, well, for much of the year anyway. I think you beat us out in the monsoon season. But what we do have in great abundance is wind power. We have lots and lots of offshore wind farms that work day and night, provided there's a good, strong breeze. However, eventually the wind stops, at which point we need something else to pick up the slack. With pumped hydro, we can use the renewable wind energy to pump water up into high reservoirs and then release it on demand to lower reservoirs, essentially improving the efficiency of our renewable system. And again, in Indonesia, there are similar projects happening. I think in Bali, there's something under construction at the moment. The project itself aims to increase public confidence in hydroelectricity in the UK and also globally to provide a framework for reducing negative environmental impacts of dams. So, for example, the entrapment of sediment behind dams is fairly well constrained in many cases. It's well known that there's strong sedimentation occurring behind the dams in the Citarum system. What hasn't been looked at in as much detail is what the effects of that are downstream of the dams. So what we are looking at here is the Citarum River as a case study to look above and below each dam at the mineral chemical stratigraphy of the river, so essentially the composition of the sediments, to determine what key elements that might be useful to ecosystems downstream are being trapped in the river. Hold a second. Yep. Sorry about that. So yeah, we're quantifying the downstream impact of the hydroelectric dams rather than the impact on the actual reservoir itself. And the aim here, once we have that data, is to try and develop a globally applicable methodology for reducing the negative impacts of hydroelectric dams that are put in new systems for identifying suitable. Thanks very much. I don't think anyone's ever done a presentation where all the tech works the first time. That's that's not how tech works. Yes. Anyway, moving on. To achieve these goals, we are doing a detailed survey of the sediments running downstream, as I mentioned. This generally involves collecting mud and sand core samples from various points down the river and around the dams. So, for example, in this case, we have worked between Jakarta and Bidang on the Citarum system, with an initial survey giving special attention to the geological context and the environment conducted in 2023. That focused on all three dams and down to the delta. So here you can see I've just highlighted a little on this schematic. We've aimed to sample the reservoir inlets. If possible, we've sampled above the dams, and then we've moved below the dams in a very methodical sampling regime to collect data around the infrastructure. There are some flaws with this in the field. Since we are using heavy mineral counting techniques, we require heavy minerals, which generally accumulate in sands. And particularly behind the dams, we have found that there's not very many sandbanks on the edge of a reservoir. Obviously, you tend to find a lot more mud.
Ya, sudah oke. Terima kasih.
Hop back a moment. Whilst we're trying to collect sand samples, we have had to collect a few mud samples as well. From the sand samples, we're completing heavy mineral stratigraphy. And from the mud samples, we'll be using SEM-IAGI analysis, which is an automated analysis using the scanning electron microscope, which will allow us essentially to get the compositional data from the surface of the muds, which we can't count manually as we can with the sands. And then using that data, we'll complete hydrological modeling of the Citarum catchment, incorporating the results as we go to show how the signature and the signal is being affected downstream. I'll just hop past there. So, as I mentioned, there's a key point survey completed in 2023. So we started right down in the, right up. Yeah, we started right up. Oh, are you sure that's the highlight button and not the on-off switch? No problem. I am familiar with the issues. I'll just have a drink while we wait. Okay, so 2023 field work last year. We started right the way up in the top of the catchment at the source of the Citarum and worked our way up through a few key points in Banten and then down the river to sample above and below each of the 3 reservoirs. When we completed that, we took a little skip to the end of the catchment to see what was happening out on the delta, hopefully pick up how much sediment is making it down. But obviously this is quite a long gap, which is something we've addressed this year. And we did have a little bit of spare time last year, so we just, as an extra little scientific interest point, hopped over to Thousand Islands. My supervisor, Amy Goff, thought she'd seen some heavy mineral lines in the sands there, so we went to take some samples to see whether they were there and whether that was material washing out from the Citarum or locally derived from the rocks offshore. Those ones I haven't actually analysed yet. They're ready. I've counted everything on the river, but the Thousand Islands was a little extra, so I'm waiting to look at it when I have a little more time. So just a slightly clearer map highlighting the points. Once again, we did start just off the bottom of the map there, and then we sampled just before the entrance to Sagaling, and then above and below the dam, in between Chirata and Sagaling, above and below the dam, and then we did visit above the Jatalaher Dam, but we weren't able to get a sand sample above it last year. So we just sampled below the dam, and we also sampled one tributary coming into the river before heading up to the delta. But that just highlights the key focus of the study. We're looking above and below the dams at the infrastructure predominantly. Some of these sections were very, very nice. So this is Green Canyon, just below Sagaling Dam, I believe, which was a very nice stretch of river. Really enjoyed heading down there to sample. There was some lovely sand. And then there were some not so nice bits where we did run into the pollution, which obviously isn't the focus of the study, but we do, sampling sediment on the river, it's inevitable that you are going to have to sample some areas that Citarum Harum hasn't quite reached yet, or is having to clean up regularly. So this particular photo is just near the inlet to Wadok Sagaling, and essentially all the litter that's coming down the river and is making it into the lake is eddying, just gathering in eddies off to the side, which is unfortunate, but we were still able to sample the area. And that brings us on to what do we do with the samples when we get back. So my primary mode of analysis is heavy mineral stratigraphy. This is a method that can be done on most sands, anything that has heavy minerals in, which are essentially, they're defined as relatively heavy really. So it's any mineral with a density greater than 2.8 grams per mil, which is the density of the liquid we use to separate them. They are used as proxies. Oh, apologies, apparently we're not using video. Yeah, there we go. My apologies, that must have happened when the wire came undone. Yes, so we will produce heavy mineral signatures from all of the samples. We've already done that for 2023. Those heavy mineral signatures are then used as proxies for the composition of the whole sediment of the river. So any sample we take ideally wants to be representative of the sediment going down at a location. We need to avoid things like sediment, like particular placer deposits, essentially of a specific heavier mineral, to avoid bias. And this allows us to get the bulk data down to a manageable level from which we can then make assessments. And the signatures that we get represent associations with various bedrock lithologies. So it's used for provenance in that way. For example, where you see a lot of quartz, mica, and feldspar, although you wouldn't be likely to get too much quartz in the heavy mineral separates, and in our case, the feldspar again would be out. But that sort of combination, you would go, that's granite, that's rhyolite. I've realized looking at it now, that was a very bad example to pick, because 2 of the 3 minerals I selected will be filtered out in the sample preparation process. So when you go through heavy mineral separation, there's a few steps just before you start. Firstly, you need to rinse off the sample. That's down to where we're working in the Citarum. Obviously, there are still a lot of pollutants, even though they're being cleaned up quite well. So the first thing we do is we take a large bucket, we dump the sample in, and we just run a slow agitating flow of water through the bottom of the sample, which lifts any pollutants out. They flow off the top and steadily clean it out. And to make sure everything's absolutely clean, once that's done, you chuck it in the microwave. Just 30 seconds, 2 minutes, that's that sort of time, completely kill anything that's in there. And if you haven't rinsed your sample well enough, you will know, because at this point, the whole lab will smell if you've not gone far enough. With that done, you move on to wet sieving and then cleaning. So with the wet sieve, we want to separate to 63 to 125 microns. This gives us a nice consistent grain size to make slides with later. Too much variation, you'll struggle to put the glass over the top and get a good representative scatter of grains. We then rinse the samples in ultrasonic baths to remove all of the clays using sodium hexametaphosphate, which is a chemical which the name is now burned into my mind, but it took me a very long time to get that lodged in my head when I was first using it. This particular section looks very simple and it's not very exciting, but it was, I think, the most time-consuming part of processing anything from the Citarum, just due to the sheer quantity of clay load in the river. And we're looking ideally to take it from the top image there on the left, on the left, where you can see it's quite muddy and dark still, and that's after probably a couple of hours of cleaning, until it's nice and clear like this. So that's the same sample, probably another 100 rinses later, which can take quite a long time. But once it's done, you get to the last stage, which is the actual separation of the heavy minerals. By this point, you've removed all the clay. You just got a nice pile of sand. Firstly, you want to take a little magnet and you just run it over to take out the iron minerals. In the Citarum, you can use a hand magnet. For other samples, if you're expecting more iron minerals, you might want to use a larger magnetic separator, but we've got away with a hand magnet so far. And then you use LST fast float heavy liquid, which is essentially just a very dense liquid in which your quartz and your lighter minerals will all float, and the heavy minerals we're interested in will sink to the bottom. So we use a nice conical funnel, as you can see there on the left, and essentially pipette the sample, titrate the sample out of the bottom, leaving the lighter minerals at the top. With that, we can then mount them to slides. There's a few key points here. So we use just a glass slide with some Canada balsam to stick the samples down. But at the stage of making the slides, you need to avoid bias as much as possible. So here's one of the slides completed. It's they can be quite pretty, but in here you've got some nice, you can see a little bit of hornblende just up there on the left where the pointer is. Another little bit down there. There's, I think, some pyroxenes down in this area. There's one. In the case of these samples, we see a lot of hornblende and pyroxene. That's you tend to get a few minerals that you see regularly. Is another one. That's just the cross-polarized light image, and again, it's quite pretty. You get another little hornblende in here. That one, that's a bit of a mess. That's probably a thick pyroxene, but I'd have to double check. I quite like this section. So you've graded your slides, you get to have a lovely look at them, and I always think they're quite pretty. However, it's very easy when you get counting to get a little bit carried away, because you'll be counting 200 grains per slide that you've made. And in my case, I had, I think, 16 or 17 slides this year, so you'll be sat counting a few thousand grains over the course of days or weeks, and you can go a little bit mad with it. As I say, bias has to be eliminated when you make the slide. To achieve that, you scatter the minerals very carefully. You essentially hold the tray of minerals, put the glue on the slide, and you just sort of hit your own arm, just like that, to scatter the minerals without allowing any sorting during the pour. When you come to counting, you continue to try and eliminate bias. To that end, you don't pick and count the easiest grain, because that's very tempting, but you will always pick the nicest grain, and it's likely to be quite often the same few minerals that have very nice, pretty grains. To achieve that, we use a mechanical stage on the microscope, moving it just 1 millimeter at a time, and then we count the grain that's nearest to the crosshair. So if I pop back a second, in this case, we would be looking, that's not the right button, that one. We would be looking at this grain here specifically, and we would ignore everything else because that is nearest to our crosshair. I'd also zoom in a little bit, but you can't pick the nice ones. You've got to pick the ugly one, unfortunately, just because it's nearest. And as I say, you continue this for a few thousand grains until you go slightly mad. Here's some of the minerals that we're interested in. Of these, obviously, we're looking at the environmental aspects, so there's a few key minerals in here which tell us a few things. So we have a couple of specific categories, phosphate minerals and potassium minerals, which will break down into non-organic nutrients in environments downstream, provided they can get there. So in the case of the phosphites, we have monazite, apatite, and xenotime, which were all fairly minor minerals in this study, but they do appear in most samples. And then for the potassium minerals, we have mica and amphiboles, which break down to give you the potassiums. Potassium feldspar would obviously be a major one, but that tends to break down into clay minerals, and we don't see it in the heavy mineral slides, unfortunately. But we do have the occasional mica, and we did have quite a lot of amphibole, particularly hornblends, throughout this one. Yeah, and there's a few more examples of some nice minerals. So we've got apatite up on the left. You can see it's got a nice high relief in the plain polarized light and very bright white in the cross polarized. The tourmaline and zircon both show nice vivid colors variously. Unlike with your standard thin section, which you would know the thickness of, in this case, we know the grains are 63 to 125 microns, but that still leaves a lot of variation, and it's a lot thicker than a usual geological 30 micron slide. So while we do look at the birefringence and the polarization colors, they need to be taken with a pinch of salt, because depending on the thickness of the grain, you will see completely different colors or different intensities. There tend to be characteristic colors that you can go through and look for. So if you have a look at the zircon here, you can see that in this case, it's nice and green. You've got a couple of bright red pinky bits where there's chips in the grain. But if I hop forward a slide, this is another very nice zircon, and this one, it's a little bit pink, a little bit purpley in the plain polarized, and you can see the green is there in the cross polarized light, but it's very, very faint. And then you get the pink and the green coming in where the grain thins out at the bottom end. Yeah, so it's a little bit more free and loose. And then you have things like these hornblends here. I've blown these up quite large, mainly because I keep saying you go slightly mad when you've been counting them for a while. I start seeing these, and my imagination starts running away because I've been staring down a microscope for 3 days at this point. And I tend to go, oh, that looks a bit like something I've seen before. So I'll just put that in there as a nice little landscape for you. Yeah, and once you've got through all of that, you get to your results, which is the interesting bit. And I have a little bit of the results from last year for you. So this is just the first 3 samples that I analyzed. Full disclosure, this one at the bottom looks very interesting because it's got all different things in it. That's also the first one I did while I was training, so I'm probably going to recount that one, and I think it might be less interesting than it looks. Nevertheless, you can see we've got 2 main bars here. We've got the green and the brown. So that's our hornblends and our pyroxenes. That forms the bulk of many of the samples that we've got. So there's the full suite of samples from last year. This is arranged with the source of the river at the bottom, all the way up to the delta at the top. The pyroxenes tend to indicate your volcanic origins, which is no surprise at all in Java. And you can see just in the middle, we've got these 3 slight anomalies where we go from pyroxene-dominated samples to hornblende-dominated samples. That's a little misleading because I've thrown all the data in without context. It looks like I found a fantastic signal where I'm showing something strapped behind the dam. That's not quite the case. These 3 samples are actually taken from the same area as the lovely fossils that you have out in the foyer. So they're around Satuo Island in Sageling, and they're actually taken from the cliffs there. So they're much more mature samples. They've already been laid down, they've had time to weather, and the pyroxenes that would normally be seen in the rest of the river break down a lot faster than the hornblends do. So you've got a potential there that the reason we're seeing that bias towards hornblende is down to time and not actually down to anything to do with the river, which is unfortunate because it's a very nice signal, and I'd love it if it was relevant to me, but I think that's an artifact of the sample locality, unfortunately. That pretty much runs through where we are with the 2023 fieldwork. So we're up to this point with the sampling and the data. However, these graphs were made just before I left. So the next step after you've got this raw data, so this is just a straight representation of how many minerals I've counted. There's been no reduction of the data, and there's been no interpretation at this stage. The next thing you would do is what's called heavy mineral indices. So you'd look at the ratios of specific minerals compared to each other. So apatite, zircon, and tourmaline, for example, which will then start to give you more information. And hopefully, if I'm back next year, I'll be able to go into some detail on that because I'll have done the analysis. But that's one of my first jobs when I get home, is to dive into that. That brings us on to what I'm doing here this year. So obviously that first little run through the fieldwork I showed you, it was very rough and ready, essentially. It went through the main dams and it hit the key points, and then we went to look at some of the wider context at localities off the river without sampling. But it does leave a lot of large gaps, which you've seen. So the aims this year were to fill in some of those gaps on the channel that we left in 2023, and to give some special attention to the tributaries joining the river and to the smaller infrastructure on the river as well. So in the case of the tributaries, obviously we've looked at the dams, we've looked at the sediment going into the river, but due to the fact that not much sand is making it to the dam itself in many cases, certainly not to the top shoreline that we can reach to sample, a lot of our sand samples were at the start of the reservoir and then below the dam. We failed to get something behind the dam, which means that that is completely ignoring all of the rivers that are joining the reservoirs. So we want to know what the influence is of tributaries adding sediment rather than just the dams taking away. We can't understand what the dams are doing if we don't understand what the whole river's doing. We need to look at the wider picture. So the aim this year is to gain that wider context. To that end, this is actually a combined map of our plans for this year and for next year. So this year we have focused on the localities up here around Bandung, the localities in between the dams at the tributaries, and this longer section running through from Jatiluhur to the Karawang area, and then spaced out down to the delta just to fill in the gaps. Next year, as I say, we'll have a look at the tributaries that are coming in on the dams themselves. So there'll be find a lovely little campsite and then hire a boat and hopefully have a lovely time sailing around the lakes for 3 weeks doing all of those samples next year. This year, however, we were focused on the river. So in 2023, our efforts to collect sand were hampered by high water levels. It'd been raining a lot, the river was very, very high, the lakes were very, very high. So we could only get to the very top of the banks where largely we were seeing muds deposited, which again is part of the reason that these samples were so spread out, because last year we were only looking at heavy mineral analysis, which requires sand. You can collect mud if you can get enough sand out of it, but there's no guarantee, and you need quite a lot of mud, which obviously we're shipping thousands of miles to London to process, which is expensive if you start picking up kilos and kilos of mud. So this year we've moved the field season to the end of August for low water levels. That's a tiny little white light. It was planned to be later than last year, but not quite this late. We had a bit of a fight with the visa application process, as we do every year. And there's a new discovery now that we are here in August, which is that the lowlands are far too hot for a pale Englishman like me. I was absolutely dying down there. I'd much prefer it up here. It's just cool enough for me to cope. But you can just little shot of Chirata down there. You can see the different heights the water levels taken in the lines that are drawn up on the dam. And I think last year when we came, it was probably in the region of that darker line just there. So sampling method for this year, for the heavy mineral counts again, we need generally 100 to 200 grams of sand minimum. And we need them to be representative of the composition of the river sediments. So what we've been sampling in is these water bottles. As soon as we finish one, it goes in the bag for a sample. So you can get, these are 600 mils, so you can get a good few hundred grams of sand in there quite nicely. And they seal up very well to be shipped back home. And for the representation, one of the main questions that I've been asked when I've been presenting last year's field work is, how are we dealing with bias in the sample itself, in the actual position we're collecting the sample? So last year we were using trench sampling. We would dig a pit and we would take some sand from usually around 10 centimeters down. The question that was raised is, well, on a river, you're sampling sandbars, point bars, sand structures like that, where inherently they are a sorting of the sediment in the river. So you have lots of clay running down the river, and the sand being carried with it, and we're looking for where the sand has accumulated without the clay. That in itself is a form of sorting which generates a form of bias. And within those sandbars, again, you get essentially placer deposits, as it were, of certain heavy minerals in some cases when the conditions are right. So we need to try and avoid only sampling one of those deposits. There was one main method that was suggested to me for countering this, which was to pick a sandbar and take 5, 10, 12 samples across the surface of the sandbar, and then either analyze them all or mix them together and then average it out. The problem with this is it means either analyzing 5, 10, or 12 samples for one locality, or taking quite a lot more material than is necessary and shipping that back home. To that end, we've tried a different method. So this is not the best photo, for which I apologize, but I think you can just about make out. This is a trench from one of our first localities this year. You can see the scale there in centimeters just on the card. So we're about, I think, 10 or 20 centimeters deep here. And you can see there's, overall, the whole thing is quite a sort of reddish brown. And then there's these darker horizons visible that you can see. So those could be representing events at different energy levels, and essentially what they're marking really is time intervals and different deposition. So I've highlighted them a little bit just because they're hard to see. Our idea here was that if we take a sediment core and we drill down through the sandbank, we're going to cross all of these layers. As the sandbars migrated back and forth, it's going to leave behind layers like this, or as they build up, again, you'll have different energy conditions, different deposition going on in those periods between the red lines. So by sampling all of them with a sediment core in one sample, hopefully we can reproduce the same effect as sampling across the sandbank to get a more representative sample. So to that end, we've used sediment core across the banks. We have Ispraham Hikmi here, who was very helpful in assisting me in the field, driving our sediment core down into the dirt. And in front, you can see there's some layers visible at the top here. This tape measure is set to 1 meter long. So that gives you an idea of scale. And then again, you can see some of the layers in the sand poking out here. There's a nice dark horizon. And by going down just 30 centimeters even, then we can cut through a good number of those layers and create a representative sample. The majority of our intact cores that we pulled out were mud. We were usually able to get some sediment out. Unfortunately, we had some issue with the design of our core, which we've tweaked as the survey went on. But regardless, even if it mixed coming out of the core, we had managed to sample through the layers, which was the goal. In the case of the mud, we did get a few quite nice ones. On average, usually 20, 25 centimeters of core. And when sampling that, if possible, we'd keep the whole thing. If we couldn't keep the whole thing for whatever reason, then we'd try to take at least a minimum of 10 centimeters depth to make sure that we were getting that spread of data that we need. And then onto the sampling localities this year, targeting smaller infrastructure, as I say. So that's places like Bandung Walaha here, which is the most Dutch dam I have ever seen. But it's a lovely little spot. We managed to get the sample above this dam, and then the second thing we did was target tributaries, and if possible, once again, target the sandbanks. So we still primarily want to rely on SEM-IAGI. Sorry, we still primarily want to rely on heavy mineral counting. But if we can't get sand, we can only get mud. That's where we can do SEM-IAGI analysis on the mud, which will allow us to still get some data from those localities. So at Bandung Walaha again, if I come on, might just run out of battery. Or the laptop's frozen. There we go. Yeah, so this is just downstream of Bandung Walaha. So we've got a lovely, great sandbank in the middle of the river. And ideally, that's where we want to sample from, over there on the other side. There's two reasons for this. Firstly, as I say, we're aiming for sandbanks if possible, and the middle of the channel tends to have the best sand. Secondly, all the way up this side is part of Citarum River's Sector 18, I think, where they are building new levees and working on the bank, which means there's going to be, anywhere up this side, there is definitely going to be a lot of new material incorporated locally into the river, rather than any information on what's being brought past the dam. So we hope that by going around to the far side of the sandbank, hopefully we'll get rid of some of that bias. That is something that we'll still need to be aware of on that sample. It was quite entertaining to get to. We had to hire one of the local fishermen with his polystyrene raft to take one of us round there and grab the core and bring it back. And here's another nice locality. So again, this shows the issue we had last year, really. This whole section is maybe the edge of it is what we'd have had access to last year, which would have just been mud. But this year, we were able to get out over here, where there were some lovely sandbanks. And what lies just off this slide, and I know, unfortunately, we didn't get a picture because we were too distracted, is just about here was the first place that I managed to get myself completely stuck in the mud and had to try and drag myself out of it again. Again, I'd love to show you a picture of that, but sadly, no one took a photo. Second thing that we've done this year, and again, we did this last year as well, was we ran a second study alongside with Hazel Beaumont, looking at microplastics. And we did a small amount of microplastic sampling this year. The actual sampling method doesn't differ too much from looking at the sediments. In the case of microplastics, we can't use plastic containers. You need to use metal containers, ideally, so that you're not contaminating the sample with the plastic itself. So if we put the microplastics into a bottle like this one, then that bottle is going to contaminate it. On top of that, you need to take note of any clothes that might have plastic fibers that participants are wearing. So you need to actually think about what you put on in the morning. And it is fine to be wearing artificial fiber clothing. You just need to take a note that it has been used. And again, same with the tools that you're using to do the sampling. If it's plastic, you need to make a note. In this case, we did 3 additional samples on the south bank of Jatlaher, nice and quickly. But that's just an extra little study that's going on the side. So this year we had 58 sediment and rock samples over 71 localities. And today, one underprepared presentation, because originally I was expecting to be in the field until tomorrow, but we managed to go quite fast on the sampling, and I threw everything here together last night. So if it's a bit rough and ready, I apologize for that, but I think I've hit all the key points, although I think I might also have gone through it faster than I meant to. Future work, obviously when we get home, I have 2023's data reduction to do and actually get some interesting information to talk to you about next year out of there. And then we have the 2024 sample preparation to do, heavy mineral analysis and hydrological modeling again. And then we'll move on to the SEM and EDX automated analysis of the muds. We should also be able to do that on the sands, but if we do, we need to be able to confirm with our manual counting that it's giving us good numbers, that we're getting a correct ratio, and then we can move on to doing automated samples and produce much more data much faster. And we'll add all of that onto the hydrological models and pull out the data. After that, we get to the interesting part that I don't know enough about yet, which is how do we incorporate this into an actual solution if we do find that there is a major issue with these non-organic nutrients and other important elements not making it downstream, for which I will be liaising with the engineering department at Heriot-Watt in the coming year, I hope. But thank you very much for coming, and I'll be happy to take any questions and elaborate on any section of that. I tried to do a broad overview of everything that we've done so that you know what we talked about, and as I say, I can hopefully add on to anything, depending on what people are interested in hearing.
Thank you so much, Mr. Samuel. Okay, ladies and gentlemen, now we will have a discussion session. So if you have any opinions or any questions regarding the presentations or maybe the future collaboration, please share your idea. And for the Zoom audience, you can use the raise hand feature on the Zoom if you want to ask or discuss something. Thank you. Any question? Okay, maybe I want to know about something about the representative sample, Mr. So how you select the representative location sample? Because we know we have Citarum River is so long channel river. So how you select from the upstream until the downstream, and after that you can summarize that you have just 71 locality sample, right? Yeah. How you, maybe you can tell to us about your opinion to select the locality sample.
I'll just flick back to a helpful slide if I can. Get rid of that. Have one of the maps, I think, would be good here. That'll do. So it's not that we need to be representative of the river as a whole. Obviously, we're expecting change down the river. That's what we want to see. So what we're looking for is representative at a given locality. So not all of these localities have been sampled. As I say, these ones around the lakes are for next year. But essentially, to try and get a good idea along the length of the river, we've tried to fill in as much distance as we can between tributaries. So you can see just here, we've gone for a very heavy, detailed section of sampling along one of the longer stretches of the river, at least up until it runs into the delta where it becomes just mainly muddy. Most of selecting a representative sample, you only want it to be representative of the location it's at. So you want to look at the local area specifically. So, yeah, here's, I've probably got a better one than that. So here's maybe one of the better examples of what we're looking for. So in this case, we're expecting bias because we have levee works on the banks. We have large diggers there moving all the soil around. That's likely to be introducing sediment to the river. That sediment, while it is being anthropogenically introduced, essentially, and it's going to be getting in greater quantities because of the works, that is still part of the signal of the river. So we want to know it's there once we're downstream. So what we'll do to get that in the sample without just getting that on its own is we'll try to go 400, 500, 600 meters, a kilometer downstream, and we'll get another sample down there after a channel has joined or after there's some works like this, where it's had time to mix in with the sediment. And then we'll look for a sandbar like we have up here on screen. So by going to the far side of that sandbar, we'd hoped to avoid this bias. We may not have succeeded, but essentially you're looking for an area where ideally it's away from any works like this. You have a natural sandbar, and then within that sandbar, you want to avoid any obvious structures that are clearly one deposit where there's a particular enrichment of a certain mineral. So in this case, where we have the darker horizon here, if I only sample that layer, then whatever that darker mineral is, we're going to see a lot more of that than there is in any of the rest of that sand. That's why we've gone for the sediment core. So essentially what that core has done is it has sampled that layer, but it's also sampled above it by several layers and below it by several layers. So essentially we've taken a mix of all the sediment from that sandbank, which is divided over time a little bit, obviously, but it means that we have a more representative idea of what sediment is present in the whole sandbank rather than just that one little layer, if that answers your question nicely. Yeah.
Okay, thank you, Mr. Samuel. I little bit understand about the, okay. So my next question is about, so we know about your research, but what the impact of your research toward the future geological knowledge, Mr.? Because I think in Indonesia, this research may be not quite often because this is maybe a little bit rare about this topic. I think, yeah, maybe you can tell us what the impact to study on this sub-study.
But essentially, towards broader geology, obviously, yes. So ideally, what this is going to do is give us a better understanding of not just what sediments are being trapped behind the dams, but what is traveling downstream. And also with the additional data being taken on the main channel, there'll be some extra data put into downstream sediment fractionation, although there's already a fair bit of literature on that point. The key point really is looking at the interaction of a live river with the hydroelectric dams with an eye to what is immediately downstream. There's been a lot of focus in the past on sediment buildup behind the dams because obviously it affects the dam's functioning. It reduces the capacity of the reservoir when sediment builds up to the rear of a dam, and then you get less use out of the reservoir. And there's been a lot of thought given to what's happening to the delta because the bulk of sand isn't reaching it. You don't have that same rebuilding of the delta. The idea here is to fill in the gap in the middle. So there's a bit of a hole in the knowledge as to how sort of agricultural environments immediately downstream and natural environments immediately downstream are being affected by the emplacement of dams holding sediment back, which may potentially have broken down to fertilize that area, and also the control of flooding, for example, reducing the amount of area that the river can actually reach effectively to deliver those sediments to. And maybe that we find that it's not an issue at all, in which case, I mean, it's not great for my PhD because I need to write about something, but excellent, no problem, brilliant. But in the UK, certainly it's a major concern. Every time somebody wants to put in a new run-of-river power station, there's local complaints, and one of the arguments that is frequently raised is what will get the effects of this going to be on the areas up and downstream of the actual infrastructure that's being put in. So by understanding that, and if there is an issue, providing solutions, we're hoping that will allow us to open up more hydroelectric potential, certainly in the UK. And as I say, if we can make a globally applicable methodology, then even in places like Indonesia, where you are still actively developing the hydroelectric, hopefully we can introduce those measures here as well and make it more sustainable in the long term. Because hydroelectric is an excellent source of clean energy. It's fairly well understood over the years, but there are still just a few little issues that hopefully we can improve upon.
Thank you, Mr. Maybe it will be our insight for our next topic in undergraduate thesis. Okay, I will give the opportunity to the room audience and Zoom meeting audience if you wanted to ask something. Okay, Jason, share your opinion or question.
So my name is My name is Gasan, and thank you for your presentation. It's really good for me. I want to ask you a question. Maybe I don't know if you have mentioned it before or not. Why you choose Citarum River to do your research? Is it because is there any special things in Citarum River, so you choose this river to do your research? Maybe that's.
Thank you, Gasan.
Yeah, that's a point that I meant to cover on one of the first slides, but I then completely forgot. So the main reason that I'm looking at Citarum rather than anything in the UK really is the fact that we're not doing anything new in the UK. So if I hop back to the start, there's a lot of slides in here. Yeah, that little comparison there. Already in Indonesia, you are outdoing us in terms of hydroelectric. I think you have a lot more potential left than we do as well. Where in the UK, we're not building new run-of-river hydroelectric systems, so there's nowhere that I can go and look at that's got new projects for me to use as an example. On top of that, we don't have anything in the UK on the same scale as the Citarum Cascade hydroelectric system. You have 3 enormous dams, one right after the other, with lovely sections of river full of sediment to sample. It's a very ideal case study for what we want to look at, essentially. And it's a lot better than any case study that we've got in the UK for the same thing. On top of that, coming over here, working with ITB, as well as being a fantastic opportunity, there is also the chance, if I want to go and look at an area where there's a new dam under construction, and maybe get some samples above and below for use in the future when the dam's finished for an immediate before and after comparison. On top of all that, you have a lot of good historic geological surveys. So there's previous data from before the dams were built and the few decades where the dams were being built that we can use in tandem with the new data we're producing as a comparison. Essentially, the Citarum it's an ideal setup for the study. There's repeated infrastructure, so we can have lots of smaller case studies to then bring together for the whole project. And we have all that wealth of background data without even having to lift a finger to get it. We just have to go and read the papers for all the historical editions. And we do have some of that in the UK, but again, our hydroelectric tends to be a lot smaller scale. So this is much more interesting for that reason, I think. Does that answer your question?
Okay, we have some audience who wants to raise hand in the Zoom. We have Ellen. Maybe you want to open camera and open the mic, Ellen.
Hi, I'm sorry, is my voice can be heard?
Okay, your voice is can hear by us.
Hi, sir. Thank you for this amazing opportunity. Sorry in advance if my question is kind of, like little bit doesn't make sense, but I have two questions. First, in terms of time, can this method predict the worst case of, like, I don't know, maybe the sediment rate is higher than the river flow rate? I mean, can this method predict any in time function and manners? And the second question is, can you please elaborate on how will you conduct the hydrogeological models that you're going to in your research plan? Thank you for the insight.
So I'll start with the second one because I can remember it immediately. So with the hydrological models, we are largely looking at inputting the data into GIS software such as ArcGIS and QGIS. Essentially, rather than doing a dynamic model, really, it's modeling to illustrate, which we'll be getting into shortly. So we'll be using maps similar to, not that one. Head through, there we are. Yeah, we'll be using maps similar to this one, but we will be taking the raw heavy mineral data that we've got, so those bar charts that I showed earlier, and we'll be looking at specific heavy mineral indices. So we'll be taking things like the apatite, zircon, tourmaline, heavy mineral indices, and how that changes over the river. So we'll model the flux in those indices, which will then allow us to interpret what's going on in the catchment, where sediment is coming from in each section of the river, to then determine what's being removed. So the function there, rather than looking at any future flux, is to use the models to really highlight and visualize what's going on in the present and what has already gone on. In the case of the second question, would you mind just repeating the first question for me?
Oh, thank you. The first question is, in terms of time function, can this method predict the worst case, like probably the time where the sediment rate is higher than the river rate, or maybe like for mitigation purposes in this time? Thank you.
I'm not sure about that one. So the purpose isn't really looking at prediction of sedimentation rates per se, as opposed to looking at the composition of what is there again. You possibly, if you had a look at the historical data, maybe you could model something, but really the idea with the heavy mineral examinations is to look at the provenance of the sediment, so you use it as a proxy to work out what the whole rocks that produced this sediment are likely to be and see where they came from. So the only way I think you'd be predicting sedimentation rates would be to do a methodical survey of the various layers within a particular area and try and establish how much was put down over a certain time frame. However, the method doesn't really, you would have to use a separate dating method anyway, in which case I think you could skip the heavy mineral section for that. So you'd probably be better looking at some sort of dating method throughout the layers to see what the accumulation rates are historically, compare them with the environmental data, and then construct a model in that way. The only flaw with that is due to significant land use change in the last few decades, there'd probably be some complications. If you used very old data, you'd need to stick to fairly recent data to get an accurate idea. Perhaps use the historical and the comparison as the land use changes to try and determine how those land use changes have affected it. But the heavy minerals itself, I don't think would be too useful for that particular prediction.
Oh, I see. Thank you so much, sir.
No problem. Thanks very much. Terry McKessie.
Thank you, Aline. And next we have Reynaldi Ramli. Okay, Reynaldi, Okay.
Yeah.
Idea Renali. Okay.
Hey Sam, it's Aldi. Hope you still remember me. So back when we took the sediment sample, the location was close to the sewage system, and there's a lot of dead fish. So, in your opinion, is there any effect of the water pollution in the Citarum River on the sediment sample of the results? It's my question.
So you were drifting away from the microphone there a little, but I think I got most of it. So for context, Aldi helped me out a little bit in the field while Isram was away and was very helpful, but also got to see some of the worst places we sampled. So a lot of the sampling locations are quite close to sewage outlets. So the pictures that I took at Sagaling, where are they? Yeah, so this site, for example, I've highlighted all the litter. This is actually a locality from last year. But 6 feet behind me, there is a sewer coming straight into the river. So a lot of the time, if you find sand, you can't really be too picky about where you sample it. It is where it is. Which does mean that a lot of our sands are contaminated with pollution, particularly sewage or pollution from the textile mills. In terms of the heavy minerals, this shouldn't have too much effect. It just brings us straight into the first stage of our sample preparation. So obviously, the heavy minerals should be unaffected by the sewage. It shouldn't be breaking them down. But it does mean that the first thing that we do when we get back is this neutralizing the sample phase, trying to get all of that really bad pollution out. So we rinse it out with water. In this case, there's a copper pipe running out of the bottom of the hose, which takes the water straight to the bottom of the sample, and that agitates the sample, allowing the pollution to be released. And you watch for it rising, and when it runs clear, you can move on to the next stage, which is, as I say, we just throw it in the microwave for a couple of minutes, just to absolutely make sure that anything that might be living in there is dead. And if it is a sewage-filled sample and you didn't rinse it for long enough, that's when you have to leave the lab for 10 minutes because you've now microwaved raw sewage, which is not great. But in terms of the data, that pollution shouldn't have too much of an effect on the actual sediment for purposes of heavy mineral separation. I think the worst effect that I've seen from pollution is actually where we were sampling litter banks. So, for example, you may remember there were some where there were bags that had filled up. Sometimes you find even in a muddy area where there's a bank of litter, if you've got a big sack or a hoodie or a jumper or some cloth that's folded up, often you actually get quite good sand accumulation inside the bag. But then you have a question of, was that trapped in there by the flow of the sediment? Was that dumped there full in the case of, for example, cement bags? Often those cement bags were then full of sand, which would suggest it's swapped, but you don't know whether somebody's filled it or not. So those, I have done a couple of localities where we sampled near those, and I took a sample from one of the bags so that we can compare them and see whether they're the same. But really, I think rather than the sewage being an issue, your main issue is how the actual buildup of litter is acting like a cobble bank or a sandbank, providing eddies and low energy points for the sediment to settle. Does that cover what you wanted to know?
Yeah, that's it. Thank you, Sam.
No problem. Thanks very much.
Any question more, audience? Okay. Maybe from the chat. I want to check. Okay. Oh, there is a question from Aisyah Kurata Aini. I want to ask Fitra, how do you treat the diversity in human activities along the river? For example, in highland, other sediment may be unique due to the plantation activities, and this would be different in the lowland area. Will this difference in the activities influence your main goal? Okay.
Yes, that's actually a very good question. That's one of the things we're interested in from last year. So we did notice, you obviously saw the images in Green Canyon earlier on in the presentation, where not only has the river just come out from the dam, so obviously you have any influence of the dam, it then flows very lazily through a lovely area of banana trees and rice paddies for quite some time before anything else joins it, which raises a question if it's flowing that gently most of the time, and it's flowing through those farms, does that then have a filtering effect on the sediments? It's entirely possible. It's something that we are looking to assess and haven't assessed yet. In terms of influencing the main goal, most of the study is self-referential within fairly local areas. So, for example, where we have sampled around a tributary, we've sampled above the tributary on both the main channel, the tributary coming in, and then below the confluence. So we have a sample for each section, which will show us how the heavy mineral signatures are different in the main channel and the tributary at that site, and it will then show us downstream how they're mixing. So while there are obviously anthropogenic factors in the area, human influence factors in the area, we're keeping the actual study itself on that section fairly local. It's really, I think it's going to have an effect when we then compare those whole studies to get the picture of the river in its entirety. Essentially, we've tried to get around the issue a little bit by breaking the larger study down into smaller micro studies. But yeah, I think there will definitely be an influence. So there's once you get down into Karawang, there's quite a lot of areas where there's construction on the river channel. There's banks being worked and levees being built. So you'll have anything from, you know, bricks and cinder blocks, cement, through to the local dirt and whatever's mixed in with it getting added to the channel. I think it certainly makes it a lot more complicated. And if anything, the sheer amount of land use change in the last few decades would be the primary argument against working on the Citarum. However, I think it is outweighed by the benefits that the river has to offer in terms of the infrastructure opportunities and the access as well.
Okay, any response from Aisha? Okay, thanks for the answer. Okay, you're welcome, Aisha. Maybe we can have last question from the audience on this room or on the Zoom meeting. But Sam, do you do your laboratory analysis in London, all your sample? Oh, so you bring the all samples to London, right? Okay. Okay, thank you, Sam, for the information. Okay, there is any question again? Okay. Thank you, Mr. Samuel, for the discussion, and thank you too to all the audience, ladies and gentlemen. So next, we will give some gratitude to Mr. Samuel. So we would like to present our gratitude for Mr. Samuel John Holmes. Therefore, I would like to invite Mr. Mirzam and Mr. Samuel to please stand forward. Maybe Fadli can take a photo.
Yeah, thank you for your time, and also thank you for your knowledge for our student, also from the audience that join our program.
Thank you, Mr. Mirzam. Okay, Sam, do you have any closing statement for us today?
Firstly, thank you very much for the certificate and the hammer. And I'd like to thank everybody for coming along to listen. It's very good to have an audience, even if I did rush a little bit, and I hope I've done some justice to your attention. I'm really looking forward to coming back next year, and hopefully I can show you some actual finished data at that point, some analysis and some conclusions, which would be quite good.
Thank you, Sam. All the best for your fieldwork and your research. Okay, by the handover of memento from ITB, our seminar has come to an end. Please have a seat. It is our privilege to have welcomed you all to this exceptional meeting. Thank you for your participation, and we look forward to more exciting Friday seminar next time. But before we close this seminar, we can have some photo session first. Maybe we would like to invite all guests and participants to please come forward, and we can take a photo in the forward of this room. Okay, for the Zoom participants, please turn on your camera. Ayo maju yuk. Kau lihat fotoin ya, Kak. In the middle, please. It's okay. Yang kuning-kuning sini maju. Okay, thank you all. Please have a seat. Honorable guests, ladies and gentlemen, thank you for your dearest attention, either here in this room or through Zoom meeting. Good day, everyone, and see you in the next Friday seminar. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.